Alright, so today we're going to start by looking at Newton's third law. For every action force, there is an equal and opposite reaction force. So first thing we're going to do is write down what that means. Okay, let's say we've got two cars. One car moving to the right, the other car moving to the left, and they collide. What this means is the force that the first car hits the second car with is equal and opposite to the force the second car hits the first car with. Okay? They are equal and opposite forces. Let's then look at another equation that we've learned recently, the impulse momentum theorem. Okay? The impulse momentum theorem said that the change in momentum was equal to the force multiplied by how long that force was being applied, the change in time. Now, we're going to solve this equation for force. Okay, so divide both sides by the amount of time that the force is being applied, and we get the force is equal to the change in momentum over how long that force is being applied. Take this and substitute it in up here. So we end up with the change in momentum of the first car over the amount of time that this force is being applied to the second car for however long that force is being applied is equal to the change in momentum of the second car divided by the change in time for how long the second car is going to be in contact with the first car. Okay, well, the amount of time that these two cars are going to be in contact is the same. However long car 1 is in contact with car 2, it's the same as how long car 2 is in contact with car 1. So these two times are the same. I'm going to go ahead and multiply both sides of the equation by time, and we will see that time cancels out. I forgot the opposite part. Bring it down. So bring it down now. Okay. So we've got this. The change in momentum of the first is equal and opposite to the change in momentum in the second. Well, we also know that momentum is equal to mass times velocity, and that the change in momentum is equal to your final momentum minus the initial momentum. So I'm going to use those two things to go down here. So this is going to be the final momentum of the first car, which is the mass of the first car times the speed of the first car at the end, the final speed of the first car, minus the mass of the first car times the initial speed of the first car. I'm going to make sure I know this is the first car by putting a little 1 with it. Okay? That is going to be equal to the opposite of the change in momentum for the second car. So for the second car, I need to do the final momentum, so the mass of the second car times the final speed of the second car minus the mass of the second car times the initial speed of the second car. I'm going to take this equation and distribute the negative. So the left side stays the same, mass of the first car times the final speed of the first car minus the mass of the first car times the initial speed of the first car is equal to, well, now I'm going to have negative mass of the second car times the velocity of the final velocity of the second car, but plus the mass of the second car times the speed of the second car, the initial speed of the second car. And now what I'm going to do is rearrange this. I'm going to move this term to the right side by adding it, and this term to the left side by adding it. So on the left side, I'll be left with the mass of the first car times the speed of the final speed of the first car, plus, because I'm adding this to both sides, the mass of the second car multiplied by the final speed of the second car is equal to, I'm going to add this to both sides. I'm going to say the mass of the first car times the initial speed of the first car plus the mass of the second car times the initial speed of the second car. Over here I now have all my final stuff. This is the total final momentum. Okay, the momentum of both of them after the collision. This over here is the total initial momentum. Okay, it's the momentum of both before they collided. Okay, so what we see is the total initial momentum is the same as the total final momentum. What we've done is we have conserved momentum, or momentum was conserved. So this is our conservation of momentum. What it says the total momentum for a system does not change if there is no outside force. Okay, so what does that mean? Well, these can be the only two forces that I'm talking about. If I add a third force in, I need to include that in the system. Okay? Otherwise, it doesn't hold. So you need to include all the forces in your system that you're going to have.